formulas, they're the exact same thing, just different representations. C, which is concentration, is N, which is moles, divided by the volume, which is in liters. When you're measuring concentration, it's always in liters. I don't like that. I don't use that formula. I use this one. You're probably used to seeing it as capital M is equal to moles per liter. That's the one I'm going to write all the time. Okay. Capital M is molarity, MOL is moles, and it's always in liters. Concentration is always in liters, and concentration is represented by square brackets. So if I wanted the concentration of NaCl or HCl, there we go right there, you just say find HCl in square brackets, which means find the concentration of HCl. Okay? So let's do the first one here. What is the molarity of a solution made by dissolving 15 moles of sodium sulfate in enough water to make a 3-liter solution? Basically, write out your formula. M is moles per liter. How many moles do we have? 15. How many liters do we have? 3. That's going to give you 5. Yeah, 5. How many sig figs should we have? 2. 5.0 M. Okay. That's about as basic as they're going to get. All right. It would have been if we were in the pH unit, the acid bases unit. I'll save it till then. Okay. Find the concentration of HCl. If 73 grams of HCl is dissolved in 4 liters of water. What's the problem with this question? Yeah. We have grams instead of moles. If they're talking about concentration, we want moles. So how do I convert 73 grams of HCl into moles? What do I need? In unison, I like that. What's the molar mass of HCl? What? It's 36.5 because chlorine is 35.5 plus 1 for the hydrogen. .5 grams per mole. If you do it like we did yesterday in terms of stoichiometry, or a bit of stoichiometry, I'm going to take what I have, 73 grams. I know that 1 mole has a mass of 36.5 grams. And you're doing it that way because you want the grams to cancel out. So if you divide 73 by 36.5, you get 2.00, I guess. Moles of HCl. And then what? What am I trying to figure out? Concentration, which is capital M, right? The molarity and concentration are the exact same thing. It's moles divided by liters. So if I have 2 moles and I have 4 liters, that's going to give me 0.500 molar. Does that make sense? People remember doing this from Chem 11? All right. How many grams of calcium carbonate is required in order to prepare 500 mils of a 2.5 molar solution? All right. Write out your formula. Molarity is moles per liter. What do we know? I've got 2.5 molar. So that's capital M, right? I don't have moles, but I do have 500 mils. Do I want it in mils? So 500 mils is how many liters? 0.5. 0.500 to be exact. I guess actually one more zero. Liters. How do I find out the number of moles? Multiply it up, right? Yeah. So moles is going to be which gives me what does it give me? 1.25. Yep. Moles of calcium carbonate. Am I done? Why? It wants grams. You can't measure out moles in the lab. You can measure out the weight or the mass in the lab. So we need to use the molar mass of calcium carbonate, so that you're going to have 1 mole of calcium carbonate, and you need the molar mass. What's the molar mass of calcium carbonate? It's 100.1 grams. So 1.25 times 100 will give me 125 grams of calcium carbonate. Is that okay? All right. All right, a dilution. So this is basically where you take stock solution and you dilute it down, or you mix two different concentrations together. All right. This has C1 V1 equals C2 V2. The other way they write it is M1 V1 is equal to M2 V2. The molarity of the first, or MI, molarity initial, volume initial, whatever. The 1 and 2 just mean initial and final. Okay. Okay. So we need to make 4 liters of a 1.2 molar sodium chloride solution. You are given 5 molar NaCl solution. How much of that do you need? So that's your initial, right? That's what you're given, 5 molar. So that's M1. V1 is what we're trying to find out. How much do I take out of that solution to put into the other solution? Okay. The other solution needs to have M2, a concentration of 1.2 molar, and a volume of 4 liters. So what do I do to get the volume? Sorry? Yeah, so multiply those, divide by 5. All right? So V1 is going to be 1.2 molar divided by 5.0 molar. And if you do all that, you should get 0.96 liters. Is that right? Yeah. And that's the right number of sig figs because we have 2 sig figs for everything, which is 960 mils. Okay. Is this sort of bouncing around in your head again from a year ago? All right. Your job is I'll give you a few minutes to work on the next page, please. And then we'll move on to, we're doing disassociation equations. And I'll put the answer key up. It's in the classroom, but I'll put it up anyway. Okay, dissociation equations. So that's just throwing something into water and it breaks up into its ions. Okay, so iron what chloride? What iron is this? 1, 2, 3, 8, 9. What is it? It's iron 3 chloride. Okay, but it's going to break up into its individual ions. So what are we going to get? Fe plus 3, Cl minus, and we're putting it into solution. So just to be, what's the word I'm looking for? Proper. What are we going to do? What should we write? If we throw these into water, AQ for aqueous. Is that it? I'm done. Walk away. You have to balance it. Equations are basically useless unless they're balanced, right? So how do I balance it? Put a 3 right there. What is the concentration of the iron? Ion, Fe plus 3. It's 3.0. We had a 3.0 molar solution of this. Therefore, we got 3.0 molar of the iron. What's the concentration of the chlorine? It's going to be 9, right? Because for every mole of iron chloride, there's 3 chlorine atoms. So when it dissociates, it triples it. So it's going to be 3 times 3.0. So it's a 9 molar concentration of the chlorine. All right. Al2O3 dissociates into what? Aluminum plus 3 and O negative 2. What are the coefficients to balance it? How many aluminums? Need to have two aluminums and 3 oxygens. So if it's 0.95 molar aluminum oxide, I'm going to have what concentration of aluminum? Two, yeah, 2 times that, which gives me 1.9 molar, and it's 3 times that for the oxygen concentration. Which is 2.9. What is what? We're taking this solid, dumping it in water, and it dissociates into it breaks up into its ions. Because every molecule, for every molecule you have here, there's 2 aluminums, right? Pretend this is Al2O. Al2O3. This is not Al2O3, but we'll pretend that it's Al2O3. Okay? I have one molecule of this. I dump it in water, and it breaks up into its ions. I got 3 oxygens, right? And 2 aluminums. So if we had, we'll just use 1 for ease. If there was 1 molar at the beginning, and it breaks up, how many moles do I have of the aluminum once it's dissociated? 2. It doubles, right? because there's 2 molecules of aluminum in every molecule. Because this is the concentration of this molecule. I'm asking for the concentration of each ion. Yeah? Because I don't know how else to explain it other than there's like.
It's just for me, it doesn't make sense that like when you have the one molecule, it's smaller, but now that you have broken it up into smaller.
Into its smaller bits. If I have one car, how many doors does it have if you break it up into its bits? I don't know. I'm just making this up.
How many pencils do you have? Like higher ratio. So originally it was just one big pencil, okay?
Let's do another one and see if that helps. Ammonium biphosphate or hydrogen phosphate. Okay? What is this going to break up into? It doesn't break into the individual atoms. It breaks into the ions. So what ions am I going to get from whatever? Ammonium phosphate. The ammonium is a group, right? It's NH4 plus. Hydrogen phosphate is PO4 2 minus. Okay? You have to balance it. How many ammoniums? What number do I have to put in front of the ammoniums? Do I have to put anything in front of the biphosphate or the hydrogen phosphates? No, it's balanced. Okay. If it's 2.5 molar of this molecule, what is the concentration of ammonium? It will be 5 because it's 2 times that. What's the concentration of the hydrogen phosphate? 2.5. It doesn't change because the coefficient's 1. Is that okay? All right. Those are dissociation equations. If I say the word dissociation, they're breaking apart into its individual ions. All right. Now the types of reactions that we've learned in grade 11, and I assume grade 10. Do you do reaction types in grade 10? Yeah? Okay. There is synthesis, decomposition, synthesis, decomp, single replacement, double replacement, neutralization, and combustion. Okay. Synthesis. What's a synthesis reaction? 2 things become 1. You're creating something. So, do any of these have 2 things go into 1 thing? The second one, sodium and sulfur form sodium sulfide. So this is a, no, you can't write in highlighter. Synthesis reaction. Okay. But just like every chemical reaction, you have to balance it. So how do I balance this? I got 8 sulfurs on that one. So how do I make this 8 sulfurs? Put an 8 in front of it. But what does that change? It means I now have 16 sodiums. So what do I put over here? 16. Always balance the pure elements last. Okay? Let's look at the top one. We have 1 compound, molecule, element, or not element, breaking apart into 2 things. It's the reverse of a synthesis reaction. It's a decomposition reaction. How do I balance this? 2 times the silver. All right, what about number 3? So we got KOH, we got H2S. If you see OH, what is it? It's a base. OH is a base, right? If you see OH, it's base, and if something leads with a hydrogen, for the most part, it's a acid. So there's 2 ways to name this one. It's 2 things changing. All right. So this K is going to bond to that sulfur. That's how we're getting K2S. And this OH is going to pick up one of those hydrogens. And we're going to produce water. Okay. So you could call this, if it's an acid-base reaction, it's a neutralization. It's just an N, not an NR. Neutralization, but it's also a type of double replacement. Okay. Because 2 things are exchanging. I would prefer neutralization, but it is a double replacement reaction because 2 things are so. Yes. Oh yeah. Hang on. Like that, right? Thank you. Neutralization, double replacement. Okay. How do we balance this one? So we have 2 potassiums here. So if we put 2 there, okay. How many oxygens are on the left-hand, the reactant side? 2. How many are on this side? So let's put 2 there. Does that balance everything? Yeah? Does everybody agree?
Yes.
Okay. Well, let's be careful because apparently I can't balance. So. Okay. So neutralization, double replacement. If it's acid-base, we'd usually say neutralization. All right. Next one. A single element plus something else gives a single element plus something else. What type of reaction is that? Single replacement. It's one thing replacing the other. SR. All right. We got to balance this, though. If you have polyatomics, SO4s, treat it as one thing. So I have 3 SO4s on the product side. I only have 1 on this side. So if I put a 3 there, I have 3 SO4s. Then check your hydrogens. How many hydrogens do I have on the product side or the reactant side? The left side. I've got 6, right? I've only got 2 over here. So I'm going to put a 3 there. Is it balanced? What needs to be balanced? 2 on the aluminum because I've got 2 aluminums there. So I throw a 2 there. All right. Next one. HCl, CaNO3, 2, calcium nitrate. What type of reaction is this? Sorry? Double replacement. It's not a neutralization because a neutralization will always produce water and a salt. Okay? So this is just a double replacement. Can we balance it? Is that it? Just a 2 and a 2 in the front and the back? Okay. Final one. If you react a carbon, a hydrocarbon with oxygen, that is a combustion. You always produce CO2 and water. That's always the products of a combustion reaction. So this is a combustion reaction. Balancing combustion reactions can be interesting. Okay, so we'll do this one together. Leave the oxygen to the end because that's the element. Okay, so we have 5 carbons over here. I only got 1 over here, so I'm going to put a 5 there. I have 10 hydrogens on the reactant side. I only have 2 there, so if I put a 5 there, we've balanced the carbons, we've balanced the hydrogens. Now we got to look at the oxygens. You always leave oxygens for the end because you have a O2 molecule. Okay, so I have 10 and 5. I got 15 oxygens on the product side. I got 2 on that side. What am I going to do? Yes, so I'm going to use fractions, but it's the same thing. I'm going to write 15 over 2 there. Okay? Hang on, we're not done. We're not done, peoples. Okay? Now, the reason I put it over 2 is because 15 over 2 times 2, the 2's would cancel. That would give me 15 oxygens, right? Yes? Does everybody agree with that? No?
Yes, that sounds right.
We're just doing the math right now, not the chemistry. The math says this works. The chemistry is like, this is bunk. Because you can't have 15 halves of a molecule. So, how do you clear the fractions? You multiply everything by 2 and it clears all the fractions. So when you multiply everything by 2, you get 2. 2 times 15 over 2 is 15. 2 times 5 is 10. And 2 times 5 is 10. See, people? Math is your friend.
Why did we put the fraction there again?
Because I had 15. I got 5 times 2 is 10. Plus 5 more oxygens. I have 15 oxygens here. And I have 2 there.
Oh, okay.
So I do it mathematically so it works, but then in reality is you can't have half a molecule. So you just clear it by multiplying through by the denominator. Okay? So it's 2, 15, 10, 10. Yeah? All right. We'll just do one of these, and then you're going to do the rest. All right. This is what stuff's going to look like in Chem 12 a lot of the time. It's all going to be words. I know. Words? All right. So we got to write the formula, and we got to balance it, and we got to classify it. Here we go. Magnesium chloride. What's the formula for magnesium chloride? MgCl2 plus lithium Li goes to lithium chloride, which is LiCl and magnesium. What type of reaction is this? Single replacement. If you have a pure element that kicks out another element, you get one other element back. It's always single replacement. What do I have to do before I can leave this question behind? Balance it. How do I do that? Let's put a 2 there and a 2 there. Balanced and single replacement. Check. That's what you're going to do for, I'm not going to do all these. I need you to do them. You're going to do it for those, and then you're going to go on to those. All right, the next set. Oh, do you want me to do one of these ones where we predict the products? I think we should do one of those. So you're going to do that for those. You're just going to write the equation and balance it. But let's go here, and we'll do this one. We'll do number 2 on the bottom of the page where we're doing everything. Lithium oxide. What's the formula for lithium oxide? Li2O plus potassium sulfide. K2S. Okay, What type of reaction is this going to be if you have two compounds reacting? It's going to be a double replacement. So that means the metal kicks out the metal, right? So the Li2 is going to bounce the potassium. You're going to get K2O and Li2S. Is it balanced? It's balanced, isn't it? You don't even have to balance it. All right. Oh, we got to name it. That's what we got to do. What's K2O called? Potassium oxide. And Li2S is lithium sulfide. There you go. All right. So we're just writing the equation, writing the products, balancing it, writing all the names. Please finish all those questions, and that'll bring us up